Hello everyone. So today we're going to explore the core technologies and the challenge of 5G based on the paper 5G tutorial overview of standard child challenges, deployment and practice. This paper provides an in-depth analysis of 5G technology like massive MIMO, hybrid beamforming, network densification, and channel modeling. We're also discussing deployment and challenges and future directions. In addition to summarize this paper, we'll incorporate insights from related work to provide a comprehensive view of how 5G is shaping the future of wireless communication and how it paves the way for 6G. So let's dive in.
5G is a transformative technology designed to meet the rapidly growing demand for higher data speed, improved connectivity, and better energy efficiency. This paper breaks down the technology that make 5G possible and address the challenge in deploying such a complex system. It discusses first key technology like massive MIMO and hybrid beamforming. Two, network densification and its role in meeting capacity demands. Three, channel modeling for millimeter wave frequencies, efficient for predicting real-world performance. In this presentation, I will explain this core idea, expand on them with insight from related work, and highlight how 5G is setting the stage for 6G.
So let's start with the massive MIMO, one of the most critical technologies in 5G. It enables base-on stations to serve multiple users simultaneously by transmitting multiple data streams. This improves spectral efficiency, which means using the available frequency spectrum more effectively. However, implementing massive MIMO and mmWave frequencies presents significant challenges. As the number of antennas increases, so does the complexity and the cost of RF chains, which process the signals. Hybrid beamforming addresses this problem by combining digital and analog processing. For example, instead of assigning an RF chain to every antenna, HDF reduces the number of RF chains needed by using analog processing to shape the beams and digital processing to handle the data streams. This makes massive MIMO critical for mmWave systems while controlling costs.
Related work expand on this idea by introduce advanced hybrid beamforming architecture. For example, switching-based analog system diagonally allocate resource to minimize power consumption. Beam element algorithm ensure that the signal reach the intended user, even in dense urban environment. These advancements are crucial for making massive MIMO work in real-world deployment. Without them, issues like signal misalignment or inefficient resource could limit the benefit of massive MIMO, especially in crowded area where interference is high.
And then we're talking about the network decentralization. Another key aspect of 5G is network decentralization. This involves deploying many small cells or mini base stations to increase capacity and improve coverage. For example, in a dense urban area where thousands of devices are connected simultaneously, a traditional single base station could struggle to handle the load. By deploying small cells, data traffic can be distributed, ensuring faster speed and a lower latency for users. However, densification also brings challenges, primarily interference between those small cells. Advanced technologies like coordinate beamforming and interference alignments are needed to mitigate these issues.
Simulation studies has shown that coordinated beamforming significantly improves throughput in ultra-dense network. For example, when small cells work together instead of competing for resource, overall network efficiency increased. Additionally, new multiple size technology like sparkled multiple ICs, and multi-user shared ICs ensure that many users can share the same frequency without causing interference. The innovation makes densification visible, even in areas with extremely high device density, such as cities or city center.
So now let's discuss channel modeling, which is essential for designing robust 5G networks. Channel models help predict how signal behaves in different environments, such as urban areas with tall buildings or rural areas with open fields. The paper discusses three types of channel models, 3GPP type spatial models. Those are standardized and rather used for scenarios like urban and suburban deployments. Geometry-based stochastic models, those incorporate randomness to simulate real-world conditions, such as varying user locations or moving vehicles. Quanti-deterministic models, these combine deterministic and stochastic approach, balancing accuracy and computational complexity. Each model is tailored for special use cases, make them vital tools for 5G network planning.
Related work extends the discussion by addressing the unique challenge of millimeter wave propagation. For example, high frequency like millimeter wave are more susceptible to obstacles, such as wall or rain, which can weaken the signal. Material like glass or metal can cause significant penetration loss, limiting signal reach indoor. Research on T-Hertz frequency, which are critical for 6G. Building on this model, T-Hertz frequency face even greater challenge, such as molecule absorption and Doppler effect, but they also promise ultra-high data rate for future networks.
While theoretical advancements are important, real-world testing is essential to validate these ideas. Testbeds such as those at Lund University have demonstrated the critical feasible of massive MIMO and hybrid beamforming. For example, those testbeds show how beamforming can dynamically adjust to user locations, ensuring strong signal even in complex environments. Simulations also highlight the benefits of coordinated beamforming in dense networks, with measurement improvement in throughput and reliability. Measurements contained for wave systems provide valuable data in path loss, delay spread, and other key factors, helping refine theoretical models.
Looking beyond 5G, we see the rise of T-Hertz frequency as a foundation for 6G. This frequency offers enormous bandwidth, enable applications like augmented reality, holographic communication, and real-time medicine images. However, T-Hertz communication comes with unique challenges. High free space path loss, and molecule absorption require advanced beamforming technique. Ultra-massive MIMO built on the principle of massive MIMO using even larger antennas array to overcome this issue. This technology will extend the capability of 5G, creating a seamless evolution toward 6G.
Although the paper provides an excellent overview of 5G, it has some limitations. So first, it lacks of quantitative data, such as real-world deployment metrics or user experience. Second, application scenarios like intelligent transportation or V2X communication are only briefly mentioned, leaving room for deeper analysis. However, related works help address those gaps, offering detailed simulations and experimental data that complements the paper's theoretical insights.
To summarize, the core technology of 5G, massive MIMO, densification, and channel modeling are interconnected. Challenge in millimeter wave like interference and high path loss inform the development of 6G technology. This advancement ensure a continuous of innovation, making a wireless network faster, more efficient, and capable of supporting future support application.
In conclusion, the paper 5G, a tutorial overview, provides a strong foundation for understanding 5G technologies and challenges. By integrating insights from related works, we explored how those technologies address current communication needs and pave the way for future advancement. The journey from 5G to 6G demonstrates a clear path of innovation, ensuring that wireless brand networks will continue to evolve to meet the demands of the future.
Here are the references for the material and research paper discussed in this presentation. This work offers valuable insight into 5G and the innovation that will shape the future of wireless communication. Thank you.